All right, so continuing in 15.2, we introduced this idea of a line integral last time. And so we're just going to continue here. Everything we talked about before was basically integrating along some line in space, or in the plane, and you thought you had this curve or this surface sitting over it, and you were kind of integrating along there. There's no reason why you can't do this same thing in 3 dimensions. What it means, visually isn't as clear, but if you got some, object snaking through 3-dimensional space, you could integrate over that as well. Maybe one way to think of a physical manifestation of that would be, right, if you had some shape moving through space and you knew its density, right, then you could integrate along that line, the density of it, and come up with it. But most of the time, there'll be other places where it shows up naturally, but most of the time, in this course, we'll just kind of give them to you. So here's a 3-dimensional example. Okay, so we want to compute the integral along some c of e to the xy ds, where c is the line segment from, we'll make it easy, 0, 0, 0 to -2, 3, -4. All right. And so in this particular case, this parameterization you can come up with for the C is pretty simple, but let's just, before we do it for this specific one, let's talk about it in general. If you got some point P here, let's say this is this point x naught, y naught, z naught, and you want the line segment that goes from P to some other Q, just say x1, y1, z1. Okay, so we came up with the equation for a line before, right, between 2 points, and what was the equation of the line? The line went, what? You went, your starting point, right, x naught plus at, and what was a? So let me write it this way. So it's x1 minus x naught, right, but let's just say that this is abc, right? That vector, then this is at, right? And then y naught plus bt, z naught plus ct. Again, this is assuming you picked this vector that's x1 minus x naught, right? y1 minus y naught. I don't want to write all that down. But if we want just the piece of the line that goes from your point P to your point Q, right? If you let t equal 0, you get your starting point, right? Your x naught, y naught, z naught. And then if you used this as your vector, the vector between the two, you'll get to the other point, right? When you let t equal 1, right? You'll have x naught, or you'll have x1 minus x naught, so they'll cancel. Does that make sense? So when you want to parameterize that line segment, you just do it the way, you just come up with the equation of your line, but then go from 0 to 1, and it should bring you from one point to another pretty easily. So in this case, what do we get for our parameterization? So our starting point is 0, right? And then since it's -2, 3, -4, that will be your vector, right? Your thing. And so the line could be, it's just -2t, 3t, -4t, and then t ranges from 0 to 1. Does that make sense? Okay. So that parameterizes your line. And now try to do what we did last time, right? So now we're just going to plug these guys in for your x, your y, and your z. Things will get more sophisticated in the next section. But I think that's all we need to do right now. So you plug those in for x, y, z, and then what's your ds? It's the magnitude of, and I guess actually we were calling this r before, right? So it's the magnitude of r prime, right? Times dt. So what is it?
-4.
Oh, -4. And then we get 16, 9, 29. Is that okay with everybody? So you end up with simply, I'll just write this one. Okay, so you integrate from 0 to 1, plug in your in your x, y, and z from the parameterizations, t, 3t, and then your ds is squared root 29. Okay? And so now we should be able to do this with just a substitution, right? You get the integral from 0 to 1 of -4t e to the 6 t squared root 29 dt.
-6t squared.
Oh, -6. Thank you. Okay. Well, that's great. Okay, so I pulled the square root of 29 out. I suppose I could have pulled the 4 out as well, but let's just do a substitution. U is -6t squared du -12t dt. If we change our bounds, right, 0 to -6, and then what does the integral become? We get, we have -4t, we want -12, so we need to put a 1/3 in, right? E to the u, and so we end up with root 29 over 3 e to the u, and then plug in your bounds. And let's see. So we end up with e to the -6 minus 1. And let's see, we end up with a negative answer. Does that make sense with our function and with our curve? So we have this function z times e to the xy. That's what we want to integrate. If that thing was always positive, your answer should be positive, but we end up with a negative. Is this negative? So z e to the xy, where do our z's go from? 0 to 1, well, 0 to -4, right? So the z's are always positive, so you should expect this thing to be, I mean, z's are always negative, so you should expect this to be negative. Okay. All right. So next bit here. All right. Okay, so we're going to talk about line integrals over vector fields here. So I guess, what do I want to say? So you have some curve here, and I don't want to draw much of a vector field, but suppose it's you have some, we'll just think some particles moving through some vector field like this, right? And so the idea, if you remember, was that work was just force. If you had a force field given by F, and then you had a direction given by a vector V, the work done in moving a particle by this force along this vector is just given by the dot product of these two things, okay? And so if you think about, you have this little curve, if you break it up into a bunch of little pieces and then just assume your direction is constant on each piece, right? That direction is essentially what your ds is representing. Your change in arc length is this distance here, right? And then you assume you're going in a constant direction there. I guess you probably want to employ the unit tangent vector there. I don't know how much I want to work through doing this. Let's just say this. So the work done on the interval, so when I say, I mean this little interval right here, should be, I don't think I even jotted this down, but it'll be the force at the point you're at, okay? So again, we're assuming this C corresponds with some parameterization R of t from A to B, okay? So the work done should be your force dotted with, let's just write it this way, the unit tangent vector times the length of that little piece of the curve. Does that make sense? So the unit tangent vector we're just using to point in the correct direction, and then we're using ds to say we're going this far along that curve. Does that make sense? And so what you end up with, well, let me just maybe write this out. So what's the equation for the tangent vector? R prime of t over magnitude of r prime of t. And what was ds? Magnitude of r prime of t dt, right? So you get those canceling out. And so in this case, everything simplifies down to this. So you get the force at your point dotted with your r prime of t dt. And I guess I've waved my hands on the integral aspect of this, but now you just say, so that's the work done on some little segment, and you add them all up, and the integral pops up, okay? And so work, the total work should be the integral from A to B of just this right here. Okay, and we'll see this can have a very different look in a minute. But this is, you see this more often than you see the line integrals that we first introduced. You see line integrals of the form given there. And so let's just do an example. Here we just will do it with brute force. Oh, and I should say, so we often will just denote this then. And this is the integral from A to B of f. Well, maybe I'll just even leave off that. The f dotted with dr. So you'll see this notation a lot, and it just means this, right? The dr is r prime dt. The f, you're evaluating it along your curve. All right, and so that's what we're going to have here. Evaluate the integral along a curve d of f dot dr, where f is this vector valued function x log y, and then y, and c is the curve, just parameterize, I'll just give you the parameterization. Okay. X equals t, y equals e to the t, and t ranges from 1 to t. So, essentially you're just, this is the line that you want to think of right here, okay? This form here. So we called it work to sort of motivate, but the idea is this is also the integral along C of f dot. Yeah, that's what we call it. So when you see this, you can think this for now, okay? And so use your parameterization. That's just take your vector field, plug in your x and y. So t goes in for x, e to the t goes in for y. Take the derivative of the r. So the r is the t, right? E to the t. Take the derivative of that and then do the dot product of the two and see what you come up with. And I think we'll do one more here. we'll go back, let's come back to that. So, try this one just following what we did there. Alright, so let's work this out. So again, this isn't, I guess this should be the working definition, at least for now, is f evaluated at your point, dotted with r prime t. In this case, are a and b, well, I'll just write out a and b. Okay, and so just to be clear, your r, right, is just the t, e to the t, right? You're just viewing that parameterization as a vector valued function instead. And so you could just plug this in. So t goes in for x, e to the t for y. Your bounds are 1 to 2. And so the f becomes what? T, yeah, t squared, I'm just going to write it this way, log of e to the t, and then e to the t, right? And then what's your r prime?
1 to e to
1 comma e to the t, right? And then dt, and so you're just doing the dot product of these. So this,
why you don't need to put RT?
say that one more time.
Why you don't need to put RT into your?
That's what this is. That's what this notation means. Take the x coordinate of rt and plug it into the x for f.
Okay. I didn't-
And then take the y. Does that make sense now?
Yeah.
So, yeah, so this, your rt is this. And so we say f of that, we mean plug that in for x, plug that in for y.
Okay. Okay.
Is that okay? So, just to be clear, this little piece is the f of rt, right? And then dotted with that little piece is the f of rt. That could be a little bit confusing. And so, I think before we do anything else, right, log of e to the t is just t, so this is t squared, e to the t dotted with this. Okay. So, do the dot product and you end up with
T
squared plus e to the 2t, is that okay? Everybody? Integrate, what do you get?
EQ over 3 plus E2 square over half.
E to
Over
the
two.
2t over 2.
Oh, yeah.
Right. Okay, and now plug in your bounds, and so you'll get what? I'll just do 8/3 minus 1/3 plus e to the 4 minus e to the 2 over 2. Is that okay? And you can just leave it in that form. Any questions? All right, so like I was saying before, most of the time we see, you're going to see line integrals. You're going to see just a function of x and y and dotted with dx. So let's just suppose we have this set up. Okay, so suppose your RT looks like this. And everything I'm doing here in 2 dimensions, you can extend to 3 dimensions. But suppose your R looks like this, right? X, T, Y, T. and then your function f, let's just say it's a function of two variables. Those functions are p and q. I'm going to drop off the p of xy and just write it as p in a second. Okay. So let's look at this for a second. Okay, so this is the line integrals we're interested in, right? And so you'll often see stuff like this, the integral from a to b of, well, what is this? This is the function pq, right? Dotted with x prime of t, y prime of t dt, right? And so that becomes integral from a to b of p x prime dt plus q y prime dt, and so again, p of xy, q of xy, but the x prime dt, that's the differential that we usually denote as dx. This is the differential we often denote as dy. Okay? And so oftentimes when we encounter these, this is the form you'll see them in. So it'll be the integral from some a to b p dx plus q dy. And again, the bounds here, the a and the b, they're bounds for that t, for that parameterization. We still need some underlying parameterization here. And maybe I'll say sometimes you'll also just see this. Right? The line integral of p dx plus q dy. Okay? All right. So let's try an example here. Evaluate this. If C is given by so, I mean, there are multiple ways to do this. You could just sort of revert back to where we started to say this is the function f is the vector field x squared plus y comma 3y, and then just do the problem the way we just did. But I would say your better bet here is to just plug in the x as 2t, your y as 3t squared, and then dy and dt to be the derivatives of those components respectively. So dx should be what?
2.
There. Yeah, x is 2t, so dx is 2,
2x.
well, 2dt. Does that make sense? So think of it like a substitution. If you would have done a substitution of x equals 2t, then dx would be 2 dt, right?
The derivative of this time dt.
Yeah, and then the same thing, right? dy 6 t dt. Does that make sense? So you'll plug these in for the dy and the dx, and plug this and this in for the x and y. Try that real quick. It should be relatively fast. work this out here. So like I said, this, that's a nice equal sign there, becomes what? The integral from 0 to 2 of
14 t squared
4 t squared plus
plus 3t squared
3t squared times
2 dt
2 dt, good, and then plus
9t squared
9t squared
times 6
6t
dt.
dt. And maybe I'll just leave it like that. I think that's easy, an easy integral, right? So now everything's just in terms of t's, just multiply it out. You got a big polynomial and you can integrate that. Okay. Let's do one last thing from this section. So here is a graph. Well, you don't really even need to know what this C1 and C2 are. But here's a bunch of information, right? So you have a curve, C1, C2, and then they give you a bunch of information up here, right? So they give you 5 different pieces of line integrals that you can compute, and then they want you to build some other ones. And we won't go through all of these. Let me just cherry pick a couple that I think would be interesting. Okay, and so let's do 51 first. So 51, it only cares about being on C1, right? And then you have f dot dr. Let's see. So they want you to evaluate this. I'm going to have to change it if we need more information and do some other orders. Oh. Okay, so our formula for this was that this is the same as what? The integral of p dx plus q dy, right? And so just like with any integral, you can think that that integral slides through. And so this should be the same as c1 p dx plus the integral over c1 q dy. And are both of those given to you? I think they are, right? C1 of p dx is, the integral over C1 is 3, and then the integral over C1 of q dy is 1. Does that make sense? And so in practice, you don't need to write any of this out. You need to just see that stuff and read it. So this should be 3 plus 1, so 4. Let's see. What's another? How about, well, let's do this one first. Let's do 50. So 50 wants the integral over all of C of Q dy. Q dy. So how do you evaluate that? So now you're -3, okay. So that's right, where did that come from then?
4 and 5.
Right, and so the point is, right, that the integral, and again, I didn't go through listing a bunch of properties of these, but they should be pretty clear, right? The integral over the whole curve, we used that fact last time, was the integral over C1 plus the integral over C2, right? So in your mind, at least, you should be viewing this as the integral over C1 of Q dy plus the integral over C2 of Q dy, and those were both given to you, 1 and -4. Does that make sense? And then maybe we'll do one other one here. I'm going to squeeze it in here so that these are all semi-close together. Let's just do 49. So what about the integral of C over C2 of p dx? So you were given the integral over C1, right? And you were given the integral over all of C. So how do you find the integral over C2?
C1 over C over C1.
C minus C1, right? Does that make sense? Right, you take you know the integral over the whole thing. If you take off the part from C1, that'll leave you with what was there from C2. And so in this case, that's what?
7 minus 3.
7 minus 3. Okay? And so, try the homework, go through some other pieces here. Be careful, as you do the homework, like some of the pieces, if 54 was assigned on its own, well, you first really have to do 50 to do the second part of 54, right? And so just be aware of that. As you go through the homework, if 1 was assigned, it might require you to do more than just that. You might not be able to read it off immediately from the 5 given. You might have to compute a couple pieces along the way. So that's the basics for line integrals. Hopefully, well, they're kind of a pain to compute, right? You have to find the t, you have to find this parameterization, and so they can be a little bit ugly. And so in the next section, we'll look at an easier way to approach them when they're nice vector fields. And so that's kind of the focus, where we move from is finding easier ways to do line integrals, and then we'll move on and look at surface integrals, and then find some easy ways to do surface integrals, when all that excitement lies ahead. We'll stop there for 15 more.